Hello. Let's wrap up this section on continuity. Here's part 2 of the video. So you may have noticed before when we were talking about zones of continuity, we were talking about an open interval. An open interval is one that does not include its endpoints. Right? So just as a quick refresher, an open interval, we write those with parentheses, and we might write it like this. This means that x is between 2 and 7, strictly between. 2 is not actually part of this, and 7 is not actually part of this. The other kind of interval that comes up a lot is a closed interval. A closed interval is written with square brackets. And when we are talking about a closed interval, those endpoints are included. So the closed interval is 2 and 7 and anything in between. The open interval is just the things strictly between 2 and 7. So we'll extend our idea of talking about being continuous on a particular zone or interval, but with closed intervals, it's a little more complicated. So I'm just going to draw a picture first. Let's draw a picture like so. And suppose here's x equals 1, and here's x equals 8. And we're going to draw the graph of y equals f of x. And let's suppose it looks like this. And pay attention to what I'm doing right now. I have just some point at x equals 1, some point at x equals 8. And in between, the graph is continuous. I connected those 2 points without lifting my stylus. And even if there was a jump right here and the graph went in a different way, and a jump right here and the graph went in a different way, it still really feels like if I ignore that and I really just focus on what happens starting at x equals 1, I don't care what happens before that, and ending at x equals 8, I don't care what happens after that. It really does feel like this function is nice if we very carefully start at x equals 1, ignoring stuff before that, and end at x equals 8. Here's what actually is happening if we want to talk about what we're noticing here. At the left endpoint, so our left endpoint is x equals 1, the limit of this function from the right, I don't care about from the left, but if I am simply approaching 1 from the right side, from the positive side, that's the same as f of 1. I acknowledge that I'm not doing the full limit. I'm not approaching from both sides at the same time. But just coming in from here, coming in from the interval, right? We only really care about stuff between 1 and 8. This stuff is irrelevant to us. So I'm just coming in from the interval. If I come in from the rest of the interval, what I am approaching is the same as what I have. If I look at the other side, at the right endpoint, it's in reverse. Here's my right endpoint. Here is the stuff approaching that from within the interval. So in this case, we're approaching from the left. We're approaching x equals 8 from the left. And that's the same as the actual y value we have. Right? I don't know what that y value is, but I know the y value I am approaching is the same as the y value I get. And then anywhere strictly in between, it's continuous, right? Continuous here and here and here and here and here and here. So it's continuous at all of these places in between. At the left end point, it's continuous in the way we care about because of the interval. On the right end, it's what we care about in terms of the interval. There we can say that this function f is continuous on the closed interval from 1 to 8. Oh, so I actually had in mind an example here with 3 to 10. Let's just change that to 1 to 8. I don't really care if you memorize all of this, but I want you to know what it looks like. If we're very strictly starting at this endpoint and ending at that endpoint, we can draw that portion of the graph without lifting our pencil, even if we'd have to immediately lift it to keep going. That's the notion of continuity on a closed interval. Okay, one last piece of vocabulary. If the limit of the function has a numerical value, but the function is not continuous because of a hole in the graph. I've just gotten this far. Let's draw a little picture. Let's suppose here is my function y equals g of x. Here's x equals 5. And as I approach 5, it's very clear that there's a y value that I'm heading towards. Right? Heading towards this y value, heading towards this y value. But it's missing, right? F of 5 just doesn't have a value. That point I'm heading towards is missing. So what we can observe here is that the limit as x approaches 5 of f of x has a numerical value. But it's not f of 5. Right? In this case, it's because f of 5 doesn't even exist. Maybe f of 5 is some other number. Right? But we have a limit. We feel like near this point, everything's super nice. It's just that at that point, something really strange is going on. Right? The very informal term for this is a hole in the graph. That's not very technical, but people use this all the time. It's one little missing point. So when we have that, when we have a hole in the graph, there is a limit, but something is wrong. The formal term for a hole in the graph is a removable discontinuity. Right? We're using this word remove because the idea is this problem is really, really minor. I could fix this function with a single point. Right? I have a discontinuity, but if I fill in that point, I remove the problem. So that's called a removable discontinuity. Technically, the function is discontinuous, but the issue is really minor and we could fix it with a single dot. That's called a removable discontinuity. Any other discontinuity is called a non-removable discontinuity. A good example of a non-removable discontinuity would be a jump in the graph. When I have a jump in the graph, I can't fix that problem with just a single point. I can't say like, oh, let's take this dot and move it up here. I'd still have a jump discontinuity. It's more fundamentally strange. Or if I have vertical asymptotes, right, I can't fix that problem by just moving one point. These are examples of non-removable discontinuities. So here's a little exercise. For each of these, first of all, just figure out where is this function discontinuous. I will tell you in each case there is a single value where it's discontinuous. If it's not obvious how to find that, go over the notes previous in this section. Then once you have that discontinuity in mind, figure out if it's removable or non-removable. So hit pause and do your best to try this. All right, so for this first one, we might remember I had this fact where I told you if it's a rational function, which all of these are, the discontinuities would only occur where the function is undefined. Oops. So here I could say R is discontinuous. CTS is a pretty standard abbreviation for continuous, so you could write DIS CTS at x equals -2. So now, if I want to know if it's removable or not, I can think about the limit of this function. Well, we're not getting 0 over 0. We're getting -2 over 0. If it's not 0 over 0, no amount of algebra is going to get us to our cancellation. So what's happening here is something fundamentally weird is going on. We actually have a vertical asymptote. So this just does not exist. It's certainly not a number if we have a vertical asymptote. So what that means is we have a non-removable discontinuity. That limit has to exist at the discontinuity to say it's removable. I think I have the graph of this ready to go. Oh no, did I lose it? I have so many windows. We'll put it in now. It was x over x plus 2. Right? At x equals -2, something weird's going on, and it's a vertical asymptote. It's so fundamentally weird that we can't fix it. Okay, how about for this example? S is discontinuous where it's undefined, so that would be at x equals, in this case, +2. So now, is there a limit at that discontinuity? And here we might notice this is a 0 over 0 example, and maybe we can do some algebra. Maybe we will notice that numerator factors, and we can cancel out what was giving us that 0 over 0 behavior. So the limit exists even though there's a discontinuity. So this is removable. X squared minus 4 over x minus 2. Let's look at the graph. X squared minus 4 over x minus 2. And there we go. This graph has a hole in it. We can't even notice. Right? Theoretically, if we zoomed in really close at x equals 2, maybe Desmos will tell us there's a problem there. Yeah, undefined. But we really can't see it. Right? It is a single point out of the infinitely many points on this line that's missing. So, this is a pretty nice function. It's technically discontinuous at a point, but not in a way that really feels like it's a problem. Right? This will be good news in calculus, like, oh, I have a problem, but it's not a real problem. I'll just do the limit. And our last example here, the discontinuity is at 1. Discontinuous at 1. Right? Because we always talk about x coordinates when we talk about continuity, you can get away with just saying it's discontinuous at 1, because we know this means x equals 1. This is another, right? If we plug this in, limit as x goes to 1, if I plug it into the top, I get 0. If I plug it into the bottom, I get 0. So I can probably do some algebra. And I'm probably going to cancel x minus 1. So let's see, can I factor it using x minus 1? I would have a 3x squared here. I would have not 3x squared, just 3x. I have a 3x there. I would have a plus 4 there. And it looks like my middle term will work out. These cancel, and that limit would be 7. Right? So there is a limit. This is also removable. Let's look at the graph for this one. 3x squared plus x minus 4 over x minus 1. Right. Again, it's one of these things where it looks just like a normal line. Technically speaking, one of the points on that line is missing, but we can't even tell. All right, now the rest in your textbook, it covers all of these things that I've covered. Then it has all these examples of functions, right? Many of which are discontinuous, right? Here's a function that you might encounter, and here's why it's discontinuous. Here's a function you might encounter, and here's why it's discontinuous. There are examples out there of things that change all at once, but we really don't need to go through all of these details. All right, I want you most of all to just understand, generally speaking, what continuity looks like in a graph. That's usually going to be enough, right? But you need to know how this vocabulary works, because we will have examples later on where, like, oh, I'm going to teach you a rule, but the rule only applies to continuous functions. So you need to be careful. Oh, I'm trying to do this problem. Am I allowed to? Is the function continuous? Well, let me look at the graph. Oh yeah, it looks continuous. I'm ready to go. So just knowing the basic idea here is what's most important moving forward. Let's not worry about analyzing function after function after function. Okay, that is it for this video.